Here's a related rates problem. Could be taken right from Calculus 1. The radius of a right circular cylinder is increasing at the rate of 6 inches per minute, and the height is decreasing by 4 inches per minute. What are the rates of change of the volume and the surface area when the radius is 12 inches, and of course decreasing by 6 inches per minute, and the height is 36 inches, and of course, the radius is increasing by 6 inches per minute, and the height is 36 inches but decreasing by 4 inches per minute. Okay, interesting question. Well, we can start with the volume of a cylinder, pi r squared h. And so differentiating with respect to t, we got dv dt here, we got the product rule applied to this. So first I'll say the derivative of the first times the second, so the derivative of pi r squared is 2 pi r times the derivative of the inside function, whatever it may be, dr dt, times h, plus the derivative of the second times the first, so that's pi r squared times dh dt. Now all this information is given, so we can just fill out. The r is 12, the height is 36, radius is 12, the height is 36. The change in the radius with respect to time is positive 6 because it's growing by 6 per minute. The radius squared is 12 squared times, of course, our perennial pi there. And then the height is decreasing by 4, so that's dh dt. And that's why it's negative. So if you do the math on that, you get 4,608 pi is the change in volume per minute at that time, which is pretty substantial. But that's a pretty substantial change with the radius growing by 6 inches per minute and the height dropping by 4 inches per minute. So what about the surface area? Well, the surface area of this cylinder, this can if you will, is going to be the area of the side plus twice the area of the ends. Okay, so that's twice the pi r squared, that's the circular end. This 2 pi r h is the height of the can, 2 pi r is the radius. If you could imagine snipping it with some tin snips and laying it out flat, it would in fact be this rectangle plus these two squares. So there we have our formula for the surface area of this. So now if I were to say, all right, then what would change in surface area with respect to time be at this moment? We could factor out the 2 pi and say that's 2 pi times, and then here we got first, actually I have second d first, here it is, d first times the second, plus derivative of the second times the first, and then plus the derivative of this term, which is 2r times dr dt being the derivative of the function r, whatever it may be. And so our change in surface area, if we simplify it a little bit, you can see we have a dr dt in two terms, so we can factor that out. We have 2h, or actually 2r's plus this h times dr dt, and this r times dh dt. And these are easily filled out. We know the radius at the time is 12, the change in the height is negative 4. Twice the radius is twice 12, and the height at that time is 36, and the change in the radius with respect to time is 6. So multiplying all this out and then multiplying that by 2 pi, the surface area is changing by 624 pi at that moment.